Welcome back to the stream. Tuco's not sitting in my chair for once. He's just sitting in a spot where there's tons of cabling and it's making me nervous. I think I've got everything cat-proofed. Welcome back to the stream. We're just getting started here. Let's go right from 0 cameras to all the cameras. See how well that works. Hello. Gosh. Tuco's always so much. I don't think he's actually biting anything at the moment. But anyway, welcome back anyone who's here. I'm mostly just picking up where I left off this yesterday. This is a bit of old technology that I'm trying to at the moment, trying to see why it's not booting. Trying to see why it's not booting reliably. This is an old voting machine that was, I think, sold in the early 2000s, but made from mostly late 90s parts. And it's having various problems. It was having some intermittent problems initializing the touchscreen, which has now become a permanent problem. I haven't seen it boot past the touchscreen initialization in quite a while at this point, and it often doesn't actually make it that far. It seems like it's getting to some point in the fairly early BIOS startup where it just decides that things aren't going well and just turns off. So we've got the PC104 connector over there populated. It was unpopulated from the factory, but it seems like the kind of thing that was designed pretty much specifically for debugging purposes. There isn't much onboard debugging that I know of. There might be some serial port debugging stuff, but I haven't really investigated that. I did notice the BIOS initializing one of the serial ports really early on, so it is possible that it does some debugging over that I haven't investigated. But I was looking for something pretty straightforward, and so I figured I would try to shoot for the port 80, port 0x80 BIOS postcode debug register. So I don't have a logic analyzer wide enough to get the whole bus, but I figured I would get at least the data bits and some of the address bits. And then we spent a bunch of time on the last stream just trying to get the logic analyzer working. I had this setup that wasn't working too well, where I was actually plugging the logic analyzer into a Raspberry Pi and then trying to run pulse view, which was just too slow. It was probably technically usable, but was just way too frustrating to use because the UI was sluggish. And I figured I wanted to mostly be doing kind of slightly higher level work using a bit of Python code to decode just the applicable parts of these bus transactions and to log that maybe in real time. That's what I was doing in the past with the hard disk bus on this same thing for debugging purposes and to get that BIOS dump. So that's what I was headed toward. And then I just had yak shaving to do, where basically, I needed to upgrade everything because it turned out my Raspberry Pi's distro was too old. So I re-imaged that Raspberry Pi this morning. It's reinstalled everything and rebuilt all the SIGROC stuff, and got the old IDE debugging decoder that I wrote for this years ago working again. Made some really trivial changes just to get it working with the new SIGROC. And it works, but the Raspberry Pi is not fast enough to run it in real time. So even without the GUI, just running the command line tools for SIGROC, I tried recompiling it again with some different compiler optimization options. Still no luck. So I just changed tactics there and plumbed the USB connection through to the VM that's running in a rack elsewhere. And so now I've got the logic analyzer connected to that VM, and we can run pulse view and SIGROC, and so that seems to work okay. I've got it capturing. I think I was capturing, if I remember right, at 8 megahertz, which is enough for this, and only using 50% CPU on this machine, so that'll be fine. We can try to move this to a more powerful machine if we need to later, but the more powerful machine is Windows, which would also work for this, honestly. We could move to Windows. I felt like using Linux for this, why not? back to the stream, everyone. Yeah, speaker gargoyle. Yes, Tuco is a speaker gargoyle. Plugged in a second keyboard, all clever here, but only one of them is actually connected to the VM. One thing about this setup that's still a little bit annoying is that I have to kind of switch places between like physical things and computer things. I think we mostly are going to be on the computer for just a minute because I basically have this hooked up and I just need to run it and see if it's working as expected. One thing we might want to do pretty soon though is connect a second logic analyzer, both to get a second opinion about what's going on here and to capture the missing parts of the bus that we're not seeing with this one logic analyzer. So yeah, okay, computer time. So yeah, welcome to the stream, everyone. I've got an old machine with a 486 single board or system on chip on it, and it's not booting reliably, and I need a bit more debug information. So I've got a logic analyzer connected to the ISA bus via the PC104 port, and I was just getting the logic analyzer set up, and I've got just a very minimal SIGROC decoder that I wrote this morning for this, and we can see if that actually works, and if not, debug it. Tuco, are you going to stand on my electronics? This is always kind of the stressful part of the stream, right? When things are just getting started out, and Tuco hasn't decided where he wants to be yet, and I've got to kind of follow him around and make sure he doesn't get into too much trouble. Cause like right in here, he could easily decide he's just gonna chew on oscilloscope knobs. Sometimes when you chews on knobs, I can replace the knobs easily. That's a really old oscilloscope, and I don't think I could replace any of those knobs, so they would just be broken. Anyway, is he gonna chill out? Maybe. Maybe I can turn on this other light now that it won't backlight my cat. Brightness. Alright. Oh, what's going on here? Oh, okay. Yeah, I was like in the middle of writing some code, and apparently one of the problems is that I used the wrong kind of else for Python. So let's fix that. Oh was having some kind of weird problem with my X server where it was acting like one of the mouse buttons slash all of the mouse buttons were getting stuck down. So hopefully we don't hit that. So I was just having to restart the X server. All right. It's annoying to adjust the camera position, but it is actually kind of cool to see Tuco from eye level, so I'm going to try moving it down. Oh. That's a good question. Have I considered making a robot to follow Tuco around while I stream? Yeah, that'd be cool. I should try that. Now that I'm in a smaller space, actually, I could use one of those pan-tilt cameras. Oh, is he going back into speaker gargoyle mode? Oh, no, don't stand on the... Tuco, don't even... Hey. Tuco. Oh, somebody is making something delicious outside. Now that the door's open, I'm getting hungry. Jump. This little tripod camera has a very similar problem to the robot camera where the camera cannot spin around 360 degrees on account of all the wires. I could make a wireless camera rig. That would be fairly annoying. I guess I'd need to run that audio through the camera instead of in through the audio interface, and then stick a wireless HDMI thing on the camera instead of an SDI thing. Put a battery on it. I don't know, I like wired stuff when possible because it's reliable and I don't have to worry about keeping stuff charged. Right. I had this working briefly, decoding these I/O writes off the bus, but I wasn't keeping track of like distinct beginning and end timestamps. So they were infinitely small in pulse view, which is always annoying. I don't know what I actually want to make the bounds like optimally, but I figured I'd start with just the duration of the actual write pulse. Technically, it might be nice to widen that out to like the actual beginning and end of the bus transaction, but like I don't have address latch enabled. I just have to like basically guess from when things are changing. That would be annoying. Anyway, I just want something simple that is not too annoying and doesn't run too slowly. So I was keeping track of some state for like what I/O operation we're inside of, which for our current purposes, we need to know the timestamp and the address and data that were latched at the beginning of that pulse. And then when the pulse ends, we can actually write the event out. Most of this is fine. Maybe I just messed up that else if. Let's try testing this in the command line before we do it in the GUI, because it might be easier to debug when things go wrong. Is that it? I mean, it's off right now, so we're not going to see any bus output. Might be a little easier to notice the state of the LCD if we have a microscope on it. Okay, I'm just gonna cycle the power switch. Alright, that definitely looked like the LCD panel changing state as soon as the power was applied. And it's in that state where it's like 300 milliamps and code from the BIOS is running. Oh, and my code crashed. That would be... It's good, I've got some input. It got far enough to crash. Oh, I should be calling reset in the constructor. Okay. It's actually not super reliable at starting the logic analyzer. So it's nice to actually have some log output from SIGROC, but I don't know if there's a useful log level in between like spewing every single time I get a block and something where I can't even tell if it's connecting. So I'm just going to assume that it's working correctly, because it seems to be when I turn on the logging, but the logging is too much to actually leave on. Oh, I think it is actually trying to do like a terminal control thing so that it can end when I press any key. So there's something in the manual about it being sensitive to any key press, which is not normally a thing that terminal apps are. And when I was running this on the Raspberry Pi, I was experiencing it just locking up the terminal. So it seemed like it was trying to do that, but it failing. And it's actually working here on my... So on the Raspberry Pi right now, I've got a top of tree git sigrok that I compiled this morning, which the Raspberry Pi is not fast enough to run. But this is just an Ubuntu Hirsute running whatever's latest in Ubuntu's repo. So this is not the sigrok that I compiled, but it still seems to be recent enough. Because Ubuntu H is more recent than Raspbian, apparently. Who would have guessed? So if that doesn't stop immediately, I'm going to assume that it's working and power cycle the board. Or not power cycle it. It's on, but it's in deep sleep. I'm going to cycle the switch on the front panel from on to off and then back to on. Don't stand on that, Tuco. No, don't even try to chomp those things. Oh, don't go up there, honey. Tuco. Tuco, you want attention, right? Yes, Tuco's a very curious cat. He's like 8 years old now, and he still has the curiosity of a kitten. Gets into all sorts of things. There isn't as much for him to get into serious trouble with here. The place I used to live had some pretty scary rafters and stuff that he would try to climb sometimes. Whereas this place is not even 2-story, and I think the most he could get into was if he somehow got into the attic or under the house or something, but I'm pretty careful to keep him from getting into that. This actually happened on stream, like 2 nights ago? I had a visit from a really curious and friendly neighbor cat, and I was trying to just give the neighbor cat some food, and the neighbor cat really insisted on checking out inside, and so we were at a different door on the house, and the neighbor cat came inside just a little bit, and then I was very carefully trying to see what happened if that cat and Tuco would see each other, and yeah, it didn't go well, so I helped the neighbor cat get out like ASAP, and Tuco does not often get along with other cats, and if we were going to do that, if we were going to have another cat here, he'd probably need a significant acclimation period, like sniffing at the other cat through the door and that kind of thing. So yeah, he's getting concerned about smells and noises outside sometimes, but he seems to really appreciate the local wildlife as long as it's, at a proper distance. I should really have a mobile light on this little camera tripod cart too, maybe. that's not a good sign that I didn't get any bus output. Oh, okay. No decoders. Huh. Decoders. So, no, it might just be something changed in like this module's interface between now and when I made this pulse view configuration. So let's just re-add this. I don't know where these defaults come from, but they definitely could be better. Yeah. Some stuff on the bus. That's what you want, right? Stuff. Could save this trace and use it to debug the decoder, probably. So I think, yeah, this pin 8 is the right strobe. So a bunch of this stuff is not even related to the I/O. Like a bunch of these are either I/O reads or they're like RAM or other peripherals that are not I/O bus mapped. This is like an x86 thing if you're not familiar, where there's like multiple different kinds of memory bus accesses. There's memory mapped stuff, which pretty much everything nowadays is, but there's also this like legacy I/O port space that has most of the original PC peripherals. So we just crashed. Wonder if we ran out of memory. Yeah, we probably ran out of memory because I didn't stop the capture. That's fine. Yeah, this is going to have a lot of like kind of old school PC peripherals that are actually in that 8-bit I/O space. It's not really 8-bit. It's the bus accesses are usually 8-bit, although newer cards use 16-bit accesses, and the addresses were always wider than 8 bits. They were like 12 bits or something. Tuco is so relaxing. Oh yeah, there's a question about how old the computer is. I should have a more exact question for this, but um, I think the actual device had like a date on it of like 2001 or so or something like that. But a lot of the components are from the late 90s. Like there's software in here that was copyright in like 1997. It's got a mix of components of fairly different ages too. Like it has an actual CPU. Like the system on chip is a lot newer than some of the components that are connected to it. The system on chip is fairly highly integrated. Like at the time that this sort of PC, like a 486 PC, would have been new, you wouldn't really have had a system on chip. It would have been like a CPU, and it would have had most of the peripherals in like a separate package, and probably I think the memory controller was in a separate package, and so you would have had to supply a bunch of support electronics to do pretty much anything. You couldn't have just taken a 486 CPU by itself and made a voting machine especially easily. So then you would have had things like laptop chipsets and like industrial chipsets come along and try to make higher levels of integration easier to build. And so this is using something from that market. Like the processor is something that would have been sold for like, I get like industrial controller kind of vibes from it mostly. But this is in kind of a weird space because it's got a lot of the same requirements as an industrial controller, where it needs to be rugged and designed by people who are like electronic systems integrators but aren't necessarily like a personal computer company. So things that are easier to integrate and kind of do more of the like kind of esoteric PC motherboard compatibility kind of stuff, like in an integrated package. I can see the appeal in that. So they started with this thing that was intended to be pretty easy to use and pretty self-contained, and low power even. Like it has all these like really low power modes where it can run at less than 1 megahertz, and it can do all of its clocking based on a 32 kilohertz crystal. It's all 3.3 volts. So, but then the system as a whole doesn't have that low power requirement because it's running off of a lead acid battery, and it needs some peripherals that the system on chip doesn't really have the horsepower to do on board. Like I think it just needs like more serial ports and parallel ports, but it also needed I don't know if the system on chip had a hard disk controller. The system on chip has this really nice flexible programmable memory controller, but they use that for the BIOS ROM and the PC card slots up here. So it's got these 3 card slots. 2 of them are full-size PC cards, and I think those are running off of the kind of fancy memory controller in the system on chip. But then it's also got this compact flash card that most of the system software is on. And so that runs off of a hard disk controller, which is external to the system on chip. I don't remember off the top of my head if the system on chip just didn't have one, or if they, like, I think at some point the number of pins on the system on chip become a limitation. And so I think if they wanted to, for example, make use of the Visa Local bus for video and the PC card memory controller, I think if they wanted those features, which require like a lot of pins, they might have had to give up some of the PC peripherals like hard disk and then get those from an external I/O chip. So they've got these external I/O chips. They've got this Super I/O chip, like literally it's called Super I/O. These were really common on computers older than this actually, as a way of combining what were previously a bunch of separate chips to do things like individual serial and parallel ports and real-time clocks and stuff. It used to be a PC motherboard would actually have separate chips for all of those things. So then you start to integrate those, and before you get to today's level of integration where you just have like the motherboard, like North Bridge and, you know, maybe a North Bridge and South Bridge, like you have, you had in the past, I think a memory controller that was still sort of a separate thing from this kind of I/O, but you had a chip that was just basically an I/O card that had a bunch of ports, but you'd stick one of those on the motherboard. So that's what we've got. I think that's running the printer, and I should really map out exactly what's on there. It's running most of the kind of wide ports that you wouldn't find on the main chip. So yeah, I think the hard disk bus, the printer, and some of the serial ports. The main other interesting thing it's got on this bus, I mean, it's got some other odds and ends that I haven't mapped out. Like it's got a PLD that probably implements some custom devices on the bus. It's got a graphics controller that hangs off of VESA local bus, which takes up a lot of the pins. That, I think they wanted that mostly because they needed something fairly beefy at the time to do responsive graphics on a 1024 by 768 panel. You know, if they were trying to use the onboard graphics controller on the system on chip, they would have been sharing RAM with the rest of the system. So that would have slowed things down dramatically, especially if they were trying to do high resolution panels. I don't think it even supported panels over quarter VGA. So they definitely needed something that wasn't the built-in chip. And then so that they have something with like a full-on 2D accelerator and a bunch of like video input and output features. So it's a little bit overkill for this application even. But yeah, VESA local bus. Haven't seen that in a while. And so I think the VESA local bus is 3.3 volts. And then everything on the system on chip is 3.3 volts, but some of the other chips are 5 volts. So I think the Super I/O chip is 5 volts only. And yeah, the graphics chip is dual voltage actually, but they're running it at 3 volts here. But then they have the expansion port, the PC104, which is where my logic analyzer is connected, and that's 5 volts because that's what the standard for that is. There's also this unknown connector that's, it looks like it might be more RAM. It looks like it might be a SIM connector, but I haven't checked to see whether it's actually a standard SIM connector for like more memory or whether it's some kind of additional expansion thing. It's positioned really nicely for if they wanted a connector that gave you access to more of like a low-level processor bus for debugging. So it might be something like that, but I'm just guessing at this point. I'm failing at making this a low commentary stream, sorry. I have an instinct to like often press enter to give myself like a space, just like mark the passage of time in the terminal. And so sometimes it throws me off when a program actually captures all the inputs unexpectedly, like this does. Just like pressing enter apparently is enough to stop it. But not just pressing enter, I think it was also, let's try just pressing space or something after it starts back up. Yeah, even just pressing space. It is switching terminal modes so that it can capture the any key. Anyway, let's see if we can decode in the terminal. Gotta watch the CPU. Okay, unlike the Raspberry Pi, we can actually run this without completely maxing out a core. Oh, Oh, there's the error. That's right, I took out the sample number. There we go, there's some bus rights. I have no idea if any of that is correct. Oh, you know what? I actually recognize some of this from the BIOS. This... what is it? Like, I don't know, this stuff looks kind of familiar. Oh, and these could be postcodes? Okay, this is all plausible so far. Like, I kind of still want a second opinion, but I also might just go with this, because this totally... oh yeah, this does look sensible. What is this? I kind of do just want to compare this with the BIOS disassembly. Well, let's try running this in Pulse View first. I don't know what it means by no decoders. Oh. That's weird. That must just be a problem with the serialization of the state or something. Like... hmm. Uh... how do I pan? Alt. I should really have a left Alt key one of these days. Okay, so this is basically the system boot. You know, the first bus activity after waking up from deep sleep. This is all stuff that is not IO port writes, but then we get some IO port writes. This first couple are OX98, which is like I don't actually know what that is. Oh, I forget if I looked for that one specifically in the documentation. Anyway, I might want to look in the data sheets to see if I can find this. I don't actually know if this is a piece of hardware that exists or if this is something debug related. But before looking up the port, I kind of want to look at the code. Cool. Good cat. Oh, why is it so tiny? The tips are too tiny anyway. So little. Maybe a little much, but whatever. So this is from the earlier BIOS extraction. Let's see, the entry point is at the very end. So when the processor boots up, this is mapped in at the bottom of memory, and it loops a few times because I think the BIOS is like 256K or something. Anyway, this ends up mapped to the top of memory also because it's looping, and the reset vector is 16 bytes before the top of memory, which is this instruction right here, which jumps here. And then this location it jumps to is actually in a table of, I don't know, just like a bunch of odds and ends. It's called the compatibility segment or compass. And that's what we've got. So we've got next giving us a jump to the actual post entry, which is where the BIOS starts, like setting up the hardware and doing a power on self-test or post. So I looked at this a little bit. There's some just like hardware setup that's based on running through tables of I/O port outs. So that's one of the first things we should be able to see. So these should be the first few instructions the CPU runs after those jumps. Should I make this even bigger? I would actually like to just scale up all of Gidra, but maybe I should DPI scale this whole machine. big. See, that's probably too big. And Ghidra still isn't bigger. I don't know if it would be if I restarted it. Ghidra's actually smaller. Gosh, yeah, it's smaller with scaling turned on. Oh, I hate it. We can go down to 720p. I think I'm just gonna crank the editor font size up and then suffer through the rest of the user interface being small. Java problems. Yeah, basically. Oh, gosh. I can't tell if I actually made it smaller. Actually, isn't there some kind of accessibility zoom on this? Maybe that's what I need. Ooh. That might be too much, right? I was wondering why it just seemed to move by itself. I have this other setting which might even be broken at the moment, but I was trying to have it automatically hide the mouse cursor when it's inactive to keep the screen less cluttered. And that might interact with this badly. Is there a shortcut for this? Like that. I don't know what that was. I'm probably gonna get annoyed with that. Do I have another Ghidra? Gosh, yeah, the zoom seems to just move to the top left when the mouse cursor hides, which is not great. Or the bottom left? Kill all Java. Okay. Yeah, this zoom is not working out. I'm just gonna turn up the editor size. Approximately 100% of the things here are too tiny, despite having at least one monitor there that's kind of big. Oh, right, I can't close the main window, even if I don't want it. Chomp, chomp, chomp. Oh, did it actually decompile that? No, that's not what I'm... It was having trouble decompiling the entry point code. It's not super surprising because it's probably messy handwritten assembly with a lot of unclear inputs and outputs. Anyway, I told it this is a function. But yeah, the decompiler is just crashing without telling me where. Anyway, we've got some old friends here, like the A20 gate, star of the show. Good old bit here in port hex 92. Oh, is that what we're doing here? 98 is... let's just pull up the documentation. So this bus goes to not only a bunch of on-chip peripherals on the main processor, but the Super I/O chip and a programmable logic chip that could basically do anything, but probably doesn't do very much. They aggressively refer to this as a microcontroller, even though it's a 486 CPU. 1996 for the processor itself. What does this mean again? Oops. Spirit, momentum, or like the run up to something like in sports. What was this running up to, I wonder? It certainly carried the momentum of the x86 instruction set, though. I'll give it that. So we have a few different kinds of registers. Are any of these memory mapped? I don't think anything here is memory mapped. These are all going through that legacy I/O space, but because the legacy I/O space is not very large, there's typically an additional level of indirection. So typically devices will use a small number of registers in that direct processor attached I/O space, the one that you would get to with the in and out instructions in x86. You'll use a small number of ports. Like typically devices will have blocks of like 4 ports or 16 ports or something. And then you'll use some of those directly, but then stuff absolutely everything you can onto another indirect thing that has usually like a register that tells you which register you're accessing, and then another indirect register that actually accesses that register. So this has multiple tables for all the different kinds of indirect registers we're dealing with. Anyway, what was I interested in? Let's just see if we can find this first access here. That's 98. I'm hoping that's something power management related, but we might just be in some kind of general purpose initialization code that doesn't relate to coming out of deep sleep. but it might just be random debugging stuff that we don't have. System control port A register. This is the one we were setting the A20 gate on. Yeah, A20 gate down there. I don't think they wanted to just add like tons of non-standard I/O ports for this system on chip design. So pretty much all the new functionality, I think like everything they added is behind a single indexed register. So where did they put that? This one, 22 and 23. So, in fact, this initialization table up here, let's see, this is a table of I/O initialization entries that are 3 bytes long. It has an I/O index and then like a mask of bits to set and bits to clear. I forget which order they come in. But these are all in that indexed space. So it'll write this byte to the index register and then use this data port to access that other thing indirectly. I'll check the Super I/O chip, but this might just be something weird. Is there not one single register list? So yeah, what all do we have on this chip? We have a keyboard interface. I think we might be using this keyboard interface because I don't think the system on chip had a... oh wait, this... Oh, this is more than just a single keyboard port. So this is PS2/AT/XT compatible, I think. There's a mouse keyboard or mouse data and clock line over here, keyboard data and clock. And then these are additional pins that back when the keyboard was a separate microcontroller on the motherboard, those would have been GPIOs on that microcontroller, and they have them broken out here as part of the keyboard interface. I have some more general purpose registers. This is a serial port. This is used for the compact flash. I don't think this IR interface is used for anything. Another serial port. Floppy drive, which is brought out to a connector, but they wouldn't have any reason to use it normally. They might have used this for debugging. Like, I don't know if they would have had any reason to want a floppy drive instead of the compact flash, though. Parallel port. Oh, and this has the real-time clock. So this thing does have a battery-backed real-time clock. Actually, I think the system on chip has one of those also, so I don't know which one they're using. Probably the system on chip. I don't remember seeing a second 32 kilohertz crystal, and the system on chip needs one of those anyway. I'm gonna see if there's just some, like, agglomerated list somebody's compiled of I/O ports, and this might give me some ideas, even though those are often, like, full of junk. I forget who's got a good one of these. Oh, OS Dev Wiki is usually a good shot. Right? Yeah, no, that's actually a good piece of advice. As an operating system developer, you shouldn't be looking for this. But it's useful for trying to understand systems that are undocumented. Oh yeah, so I'm not getting the least significant bit of this or any of the upper bits. So this could be like 99, it could be like 198, 398. Anyway, that doesn't exactly match what I would have expected to see in the BIOS. Like, this initialization table is the first thing we launch into, so I should get another trace that is not from deep sleep, but is from actually power off. Oh, actually, you know what? Never mind. From my earlier skimming of the system on chip docs, I'm pretty sure that it wouldn't have even sent the I/O to the external bus if it was handled internally. So these first couple of I/O writes are to the system on chips. I forget what they call this, but it's like their custom indexed register. And I'm remembering that there's an option in the system on chip to reflect all the on-chip stuff to the external bus, but I think that is disabled by default. And I think they might even turn that on later, but I think at this point, we just powered on, so it wouldn't be on yet. So that would explain things, maybe. You do go. So in that case, this is setting up on-chip stuff, and then we end up... These are just being used as, like, delays or, like, cache poking mechanisms of some sort, I don't know. But now we're starting to get into stuff that is suspicious, right? Like, I mean, more like PC standard IOs. I'm worried about what Tuco's doing. Oh, Tuco, where are you there? Hey, Buzzo. Okay. Alright, so this is actually stuff that could conceivably be handled on chip. So, system control register, more indexed stuff. Yeah, this is like checking to see whether the Visa local bus is like in the right default state or whether somebody's already initialized it. It's kind of weird. Oh, yeah. This is also weird. Oh, where was this pointing? Very bottom of address space. So this is very early in initialization. I don't think we've turned on... We've either just turned on DRAM or we haven't turned on DRAM yet. This is probably right after we've set up DRAM. And one of the things that it's doing is what looks like an aliasing test where it writes alternating bit patterns to the first two 16-bit words of memory and then checks to see whether they're written as expected or whether they collided. And then there's a failure path here for if that detected a collision. And this is already getting into stuff I haven't looked at all. Oh yeah, this was a port 80 output. So I still don't know where that 9.8 is coming from, but I think we saw some 80s afterwards. Is this going to be the most annoying way to look at this? So I don't super care about the timing for most of this. It might be interesting in some cases, but mostly I just want a list of these. It is actually kind of cool looking at the other address lines here, because I think these are actually being driven for memory accesses. Is that true? It wouldn't be every memory access though, because like these, I mean, I'm only sampling this at 8 megahertz, but I'm not seeing a lot of glitching. Anyway, we could try looking at this on the O-scope for a higher speed view. I think my general strategy for this is going to be O-scope for like high speed stuff and for kind of sanity checking whatever else is going on. But this setup should be good for just giving me a list of I/O accesses. So yeah, how about list? Let's just do some list. Oh. I'm gonna actually power cycle it this time. Okay, let's just end it there. Oh, there's Tuco. Tuco. Okay, so keeping in mind we don't actually know what these are. This is something that, given our low visibility into the bus, looks like OX98. If this is actually OX9, I mean, so it could be OX98, 99, 198, 199, etc. But none of those make a ton of sense as far as I know. So it's probably some extra debug hardware, and like, what are these being set to? Like a bunch of different things. Right? Like looks like it's kind of sending a whole message out that port. So just from context, like it certainly could be some debug hardware where maybe there's something capturing all of these and sending them to a FIFO and for logging purposes. Or maybe this is initialization for some piece of hardware I don't know about yet. Tuco, why are you in the box? Are you a cat? So then this might actually be OX80. I think this fits the OX80 I was seeing up here. Oh. Gosh, it's like I can't concentrate because I know Tuco's about to do something like that. Honey boy. He is looking so hard for something he can chomp on. He is also blocking the view of my monitor. Tuco. Did he just change the focus on the camera? Tuco, what are you doing? Are you trying to chomp more HDMI cables? Tuco, don't do that. Little goblin. Oh no, don't. No. Tuco, am I gonna have to kick you out? Dude. Honey bubble boy. Such cat. No. Okay, that might be this. A 2 going out to port 80. Okay, so we got a bunch of 9/8s. Some of this stuff in FA and F8. Right, and then we've got some of these like incrementing postcodes. Whereas, I don't want to get in, I don't want to bite off too much. I don't want to speculate about where I am without being sure of my debugging methods, but the part of this that's most interesting, of course, is whatever's happening right before it decides to power off. Tuka, what are you doing? Kitty. Yeah, a bunch more 8. Do we know what EC is? That's interesting, right? Like we're counting up. And it's just a big old hole in most PC I/O spaces. So yeah, one choice would be to add more probes so we can get a clearer idea of what these actually are. If I hook the logic analyzer up and did a trace on that and on here, we could figure out like specifically what these I/O ports are, at least what the numbers are. We wouldn't necessarily know what they are for. But this might already be enough to figure out roughly where in the BIOS we're getting to. To go. Don't. Hey. It's like tracing through the code by hand is fun. It might also be, might not be that hard to try running this in emulation, just to see where some of these IOs are coming from. But I doubt that's going to get very far. Like, as soon as this starts waiting on peripherals, we're going to have to start coding around that to get any kind of emulation to make progress. So I don't know whether that's going to be easier or just reading the code. Whatever I do, I've got to keep an eye on this little gremlin. Be less close to the electronics. Anyway, if we can figure out what format the code that usually writes these postcodes takes, so that we can just search for it, then we might be able to figure out at least generally where this is failing, because we've got this postcode right here at the end. This might just be like some non-standard way of having more detailed postcodes, or maybe this EC is actually the piece of hardware that it's trying to talk to. But what would it indicate progress like this for? You know, I'm thinking this is maybe like some kind of memory test or disk test or something. And maybe it's indicating status to some debug board we don't have over the pair of the standard port OX80 and whatever this actually is. I kind of want the whole address bus. We should just hook the whole address bus up to the logic analyzer. I mean, we don't need every bit for the I/O port decoding, but, you know, all the bits that are relevant to I/O ports at least. this left connector is the sort of addition that PC104 got to go from 8-bit to 16-bit. So it has the extra 8 bits of data, has some extra DMA and IRQ channels, and some extra address lines. I don't think we need any of those, though. And we've got 16 channels. I figure I'll just put the most significant bit on IO right again and put everything else on address. Which are handy, they're all in order. Okay. Tuco's in the chair that I need. Tuco, you want to switch seats? You want to sit there? Tuco, I'm offering you my seat. Yeah, it's good, right? You're gonna take it. All right. I should switch cameras. Gosh, parallel buses really lead to some mammoth logic analyzers. We could just have 2 cat cams. You can see the electronics I'm doing in those like couple of pixels of the top of the screen. The rest of it's cat. I'm just putting scope probes on this, or logic analyzer probes. I'm doubling up on, so this is the address bus only, and I'm getting 7 bits of the address bus on the other logic analyzer, so I'm sharing those pins. But then this logic analyzer will see the low 16 bits of the address bus. Gosh, I feel bad that Tuco was mean to that other friendly cat. I don't think anybody got hurt, but Tuco was not pleased that someone else was nearby. I think that other cat and I are still friends. Oh, these are going to be tight. Oh wow, 64-bit PCI X. That sounds really annoying to debug. Yeah. I was briefly tempting to try to do something with JTAG on this board. I just don't think any of the chips Like the system on chip has JTAG. I don't know if anything else has JTAG, and the system on chip has only a very limited amount of JTAG. Like, it's designed to do these slow boundary scan processes that help you make sure your board is electrically connected, but I don't think you can really functionally control anything that way. Gonna be surprised if the first time I run this I get the same bits out, because there's probably gonna be a loose wire. Maybe that's alright. Okay, that is the low byte of the address, which has most of its pins shared with the other logic analyzer. Now I can just straightforwardly stick the rest of these on. One of the many things that I should know how to do but don't is apparently, like, I would like to reset the position of all these traces. I could just do that. Okay, so we should see it decode the address in hex at the bottom, and then that top bit should be our IO write. And it's still actually unplugged. Is it actually booting? It is booting, huh. It's normal for that to display like uninitialized video memory during part of the boot up. It's kind of nice just to take in all the other bus activity that this also happens to be able to see. Incidentally, that noise that it plays when it hits the touchscreen error, I have definitely heard it play that back at completely the wrong speed. So I'm wondering if there's some kind of oscillator related problem on here. I haven't found any smoking guns for that, but it's pretty concerning. That sounded normal though. Oh. That's interesting. I didn't do that. That was it slowing down the clock, and now it doesn't seem to be doing anything on the bus. Press the reset button. Now it's actually asleep. Okay, now I can move these. I don't know why I wasn't seemingly able to move them before. Just turn off some of these. Oh yeah, I can keep those off while they're still on in the bus decoder. That's what I actually wanted. Yeah. How can I not move the bus? Maybe I can't move the bus. Am I hacking on a tablet? Sort of. It's a tablet the size of a suitcase that usually ran off of lead-acid batteries. Yeah, this looks deceptively small on the screen. It's actually really heavy, and there's a bunch of circuit boards in the back. This was in the part of the voting machine that swings up and then like locks into place. And this is the motherboard. Is this... Oh, did I not put D15 in the right spot? That's right. I was going to take the low 14, or sorry, the low 15 bits of this bus, but then actually have IO right, and I messed up my IO right, which explains why this timing is wrong. And 2 wants out now, so I'm going to let him out. Do you want out? All right. Let's fix that. Do we need to share this one? $15. Yeah. Okay, that should be better. There's that weird clock thing again. That is interesting, and it does seem to be like switching between clock frequencies at a fairly leisurely pace there. Oh, why is this low so much? Yeah, it's supposed to stay high and then just pulse low briefly. Oh, so these are... That actually makes sense. These are actually IO writes to 394, 395... 2.3? Yeah, 2.3 and 2.2 are real. We're probably not seeing IO write there because they're probably reads. Either that or we already turned off the bit that externally mirrors those IOs. This is pretty interesting, but the next thing I want to do is set it to trigger on this and address OX80. Oh. Yeah. So we saw a little more there. So the clock is just stretching and stretching and stretching, like something is failing and or is turned off. And that started happening while it was doing the touchscreen, or before it was doing the touchscreen calibration. So it makes sense that if the time base is way off of what it was expecting, that maybe it couldn't communicate with the touchscreen chip. That's interesting. I wonder if we would see that 32 kilohertz crystal do anything weird while that clock slowdown's happening. Hmm. 394. So this is probably what we were seeing on the other trace. Also, some of these high bits might not be relevant, but 3 is, or at least it should be. Oh, where are the VGA registers? That's not here, is it? Yeah, 394 is empty in this list that comes from Box. Hmm. Hmm. Oh, now it's booting. That was the highest speed yet. Hmm. I was trying to get some stuff other than just the screen in that shot, but maybe I should just focus on getting a better view of the screen. Reset button. Now it's in deep sleep. But that was some shaky clock business, right? I don't know if we would be relying on any clocks other than the main system on chip clock this early in boot. I don't even know if this thing will boot with a scope probe on the crystal. Tuco wants back in? Can't reach the door without getting up. Yeah, I should be hunting around for some good clocks that are derived from this, because I cannot measure this directly without affecting it. Let's let Tuco in. Tuco? Remote control door opener, yeah. I don't know what would be better than just the bus itself, which I've already got a pretty good view of. Might be worth poking this probe over at the oscillator for the Super I/O, because that's actually pretty easy to measure. I might just be basting this thing with EMI now. Hmm. That's what I wanted. Oh, it's post. Ah, it looks better. Yay, so now we should be seeing the same events we were seeing in the text listing, but with a lot more actual context. Like we can see what the actual pulses looked like. So we've got the 394 and 395. should have a keyboard on this side of the room, but I don't because of USB. Or because of my USB configuration. Huh. I'm wondering about these high bits. Is that really 80 or 280? We have 280 and 80. This one that's showing up as 680 on the scope, I think that's actually 280. I don't think that 6-bit is actually used for I/O addressing. But it's not 80. Okay. That's another nice clue. I guess that's the one that was being set to 55 AA. I should probably be looking at matching traces. Like have one test run that I'm getting on both logic analyzers. Okay, this ED is the one that was showing up as EC on the other logic analyzer. And here's some actual 80s. So I'm guessing that 80 and ED are both some kind of debug card, because 80 is the standard debug card, and then it seems like ED is happening kind of in the same vicinity with additional progress information. These bus cycles are sure taking different lengths of time, huh? Right? Like we were just changing the oscillator frequency, weren't we? Huh. Is the oscillator frequency supposed to be bouncing? Is it... Okay, so first we've got a glitch. And then I think that's another glitch. Then we've got an actual I/O write cycle that's more like 500 microseconds, which is pretty typical. We've got some of those 500 microsecond write cycles. Yeah, and that's what's happening there. So during this set of ED writes, it's changing. I'm assuming right now that ED is debugging, so... I don't know if they're related to these 3B and 3D4 writes, or if it's caused by something else. So it's going off the chart here. More than 2.5 microseconds, and then now we're coming back. It would explain a lot of what we're seeing if there was just a wildly unstable oscillator and it was like fluttering up and down like this without any changes. That would explain the sort of strange noises that it's been making and the touchscreen failures perhaps. And presumably the boot failures, is if clock frequency changes while we're trying to communicate with hardware, I'm sure that could cause all sorts of glitches. Yeah, see, this is why I wanted the cursor to auto-hide, but I guess it's not doing that. Okay, so what have we got so far? I don't know why I'm talking this much. This was going to be a low commentary stream, but I guess what I meant by that was I wasn't going to force it, but I guess if I feel like talking, maybe I'll talk. Yeah, so my set of assumptions here so far are that 8.0 and ED are on some kind of debug card, that these traces don't really match. Like, I don't think these are actually the same path that boot up is going through on this versus the other logic analyzer. So that's something to work on. And there was some confusing numbering here. Like, I think this first 80 might actually be 280. Or not even this. So again, on a different trace, that first 80 that was getting like that 5.5. Yeah, okay, no, here it is. I think these 80s are actually 280. Anyway. If this is just an oscillator problem, though, then we should try to find the analog source of this without going too deep into the digital. Oh, how late is it? Oh, it's not even that late. We could look at the documentation for the system on chip, maybe. Yeah, it might also just be nice to look in Gidra to see if we can find, like, I'm assuming there's a subroutine maybe that's doing these runs of 80 and ED for debugging. And if we can find that, that might be a nice clue for linking up the structure of the BIOS with what we're actually seeing here in the dump. Okay, that maybe. How much of that did I make? Okay, so I'm going to expect this to start with some noise because the bus was going through a power ramp up when all of this happened. So I'm going to use the O-scope to try to synchronize this with the beginning of the actual bus traffic. Alright, so these first two look like junk. That looks like an actual bus transaction. Also the timestamps, these first two happened like pretty much immediately, 0 seconds and 25 microseconds, and then the third one's after 1 second. So I think this will just show up as 9.4 and 9.5. Huh. Oh, we might have a problem with the setup. I should run this under pulse view, maybe. This doesn't really make any sense. Oh, it actually saved these settings this time. Oh yeah, we just ran out of memory. That was interesting for a minute. Anyway, I'm not trying to take a giant capture in pulse view because I'm just going to run out of memory that way, but I should see if this is actually working. It's a little. I don't see any bits that are just disconnected. This one's kind of suspicious. So small. It seems fine. I'm a little concerned by how pin 9 here looks a bit more sparse than the other address bits, but I think we're just seeing that a lot of the I/O ports are aligned on a multiple of 4. It does seem like this changes where we would expect the address bus to be loaded, and it's not just crosstalk from one of these other pins. Also some very distinct different regions here, like, right, this is probably BIOS and then application loading and then the error screen. Or wait, I'm getting confused. I don't know if this was a full boot or if this was one where it powered off. Ah, they're so little. I don't know why we're seeing 9.8. Yeah, 9.8 on here versus 9.4 on the scope. Let me just ditch pulse view. Pulse view is not useful for getting the big picture here. Nine eight. This is not matching up super well. Might go triple check for wiring mistakes. This timing is changing again. I think this might be a good wrap-up point for this stream. I'm a little bit out of ideas here. My traces don't quite match up, but that's not really the top of my list of concerns right now. This could just be because I'm not sampling fast enough to get all of these different states on the Logic 16, or I could have a wiring mistake. My wiring is a little iffy right now because I'm trying to share a bunch of these pins between the two logic analyzers. But I'm just way more concerned right now than I was before today's stream about this clock issue, like the frequency changing drastically during power on. I mean, I expect that to some extent, but this certainly seems like it's misbehaving. So I feel like the next thing I want to do really is just go, I don't know, treat the system on chip manual for this thing as some light bedtime reading and just collect some more ideas for what might actually be going on with the clock management here. And specifically, I'd like some better clock probes, like what are, I mean, I know a little bit about the different clock generator modes that this has, but like I would like to know how I can determine what's going on from the outside just with the pins that are available. But yeah, thanks for stopping by. I'll try to keep these streams coming on a regular basis and not worrying super much about each individual one being as long as possible, but just trying to keep them coming, like, you know, every day if possible. So we'll get back with this soon. Happy hacking, everyone, and I'll see you next time.